Alright, hopefully I get this video finished before my kids come home from my mom's house. But if you hear some kids yelling in the background, that's why. We're just going to do a problem. How much heat is required to raise 9.0 grams of ice at -5 degrees Celsius to vapor at 125 degrees Celsius. Those should have had two sig figs. Let me fix those. -5.0 degrees Celsius, sorry. And that should have been -125.0 degrees Celsius. Okay, so we're looking for the total heat to go from -5 degrees Celsius with 9 grams of ice to 125 degrees Celsius, and it's still at 9 grams of vapor. So I just reproduced the graph from the last video. You should already have it. Okay, there's 5 steps we have to go through, and I'm going to label them as Q1. That's the warming of the ice. Q2 is the melting of the ice. Okay, so let's just say warming ice to the freezing point. Okay, then we have to melt the ice. And then here, this is Q3. I have to warm the water. And Q4, we have to vaporize the water. And then finally, we have to warm the vapor, and that's going to be our Q5. And you can do this all in reverse. If the problem said how much heat is released to take the vapor down to ice, it's the exact same process. And let's just talk about these for a second. Q1, Q3, and Q5, they're going to all use Q is equal to MC delta T. Q2 and 4, and we'll talk more about each one of these as we go. Q2 and 4, they're going to use N is equal to N times the delta H. There's no delta T on 2 and 4, so we can't use Q is equal to MC delta T. Okay, so let's just go through each one of these steps one by one. So let's do Q1, the warming of the ice. So what has to happen is we have ice at -5 degrees Celsius. The ice cannot melt until it gets to its normal freezing point of 0. Okay, so we're going to use MC of ice times delta T of the ice. And the reason I make that specification is because everything is going to have, that's a loud goat, everything is going to have the same mass. The C is specific for ice, water, and the vapor, okay? Joules per gram degrees Celsius, but the units are the same, okay? 2.09 joules per gram degree Celsius, that's the heat capacity for ice. And the delta T, final temperature is 0.0 degrees Celsius for the ice, and it starts off at -5 degrees Celsius. Okay? Hopefully there shouldn't be anything surprising there. And, you know, this is just algebra, so I'm just going to give you the answer. And 94 joules to 2 sig figs. Okay? Now we've gotten that ice from 5 degrees up to our freezing point or melting point, whatever you like to think of it, of 0. So now, because there's no temperature change at this point, we need to go to N delta H of fusion. N is a 0.5 moles. Where did that come from? Well, we have 9.0 grams of H2O and 1 mole per 18.0 2 grams, that gives us 0.50 moles. Okay. And delta H of fusion, and of course all these values will be given to you. You need to know the molar mass of water, but you don't need to know the delta H of fusion for water. Okay, now Q3. Q3 is that, oh, I'm sorry, I didn't give you the answer. What is this equal to? That's 3.0 kilojoules. Okay, something to take note of already. I'm going to point out right now. We have joules and kilojoules. That's going to be something we need to take care of in the end. Q3, MC, we're going to call this C of liquid, delta T of liquid. And that is, again, 9.0 grams times 4.184 joules per gram degree Celsius. That's the heat capacity of water times the delta T. This is going to go from 0 degrees Celsius up to 100. So we have 100 minus 0. It's always final minus initial, remember. It's been a while since we did these problems. Okay, and that gives us a value of 3766 joules. Okay, again, that's in joules, so we need to remember that. Q4, let's go back up. Q4, we need to vaporize the water. Okay, so let's vaporize the water. No change in temperature, so we know we need to use N delta H of fusion. If you used Q is equal to MC delta T here, try to plug in some numbers, you'll get 0 for a delta T because it starts at 100 and ends at 100. You have 0 energy required to vaporize the water, and that means you could just set a pot of water on the stove, never turn the stove on, and you could boil pasta, and that wouldn't make any sense. Okay, so again, 0.50 moles of H2O times 40.7 kilojoules per mole, and I come out with 20.3 kilojoules. And then Q5, going back up. Q5 is to warm up that water vapor. Okay, it's going to go from 100 to 125. So again, M, C, we'll call this vapor, delta T of vapor. Okay, 9.0 grams times 2.01 joules per gram degree Celsius. And you might say, where do we get these C's when we're doing our homework? You just look them up, go in the book, Google it. It's okay to Google a constant like that. And then we have 125.0 degrees Celsius minus 100.0 degrees Celsius. And that gives us a Q of 452 joules. Now, what is our Q total? How much energy did that take? Well, we just have to add them all up. Let's see, we started with blue, Q1 plus Q2 plus Q3 plus Q4 plus, I probably don't need to do all this, but I'm just showing you, I'm going to add all of these up. I'm going to change units as I go, because I'm going to jump from joules to kilojoules. If you need help with that, go ahead and shoot me an email and I will help you with that. But what we end up with is 94 joules becomes 0.094 kilojoules plus 3.0 kilojoules stays 3.0 kilojoules plus, let's see, purple, 3766 joules becomes, to 2 sig figs, just 3.8 kilojoules plus, all of these have 2 sig figs, and if you get hung up on the sig figs, you're missing the point of this problem, okay? Next, the red 20.3 kilojoules plus, lastly, 0.45 kilojoules. Okay, and I come out with a final answer of 27.6 kilojoules. All right, go through that problem. Make sure you can do it on your own. Send me an email if you need help. Zoom meeting, office hours on Wednesday, of course, and Monday.